So the word operation is just a big word for math. So things we can do in math, some normal operations, things we can do is we can add, we can subtract, we can multiply and divide. So those are some major operations. You've also learned another one recently called an exponent. And so yes, exponent. You've also learned about the square root, but I'll show you in a minute that square roots are just exponents. In math, whenever we do math, there is something known as the order of the operations. So order of operations tells you the order that you must perform math in. Which one is the strongest? You do that one first. Then the next strongest, you do that next. And you follow the order of operations. And those are the rules that you have to follow. And you always have to do math in the order of operations. And we will talk about those. However, our goal of these notes is to solve for x. And in order to solve for x, you always do backwards order of operations. So when we do backwards order of operations, what ends up happening is that our goal to solve for x, another word for solve is to get it alone. So our goal is to get x all alone. And a big word for get it all alone is isolate. So isolate means to get alone. And then in order to get that variable alone, we have to eliminate all the things around it. So eliminate means to cancel out or get rid of. So we're going to eliminate things that are around x and make them go away so that we can isolate x to get it alone. So I told you in order to eliminate things, we're going to use backwards order of operations. However, the fancy name to eliminate something is to use the inverse. So the inverse of an operation is what you have to do to that operation to make it eliminate. So that is the easy definition of inverse. But the hard definition of inverse is this. When you have a number, star, and star means operation. Here, I'm going to write this up, operation. They use star to mean operation. So when you have a number, star, the inverse, the answer is the identity. All right, so I know that makes very little sense right now. Let's talk about the word identity, and then I'll explain what this means. So identity in an operation. So in operations, identity is something that does not change the number in the operation. So the mathematical way is if I have some number and then I do the operation with the identity, I still get the same number. It doesn't change. So let's give some examples of operation inverses using identities. So I'm going to take some number because all of these formulas say number. Let's say I take 9. And I'm going to do some operation. So remember, my operations are add, subtract, multiply, and divide. I'm going to start with add. So I'm going to add. And the identity, so I'm using this one here, whatever the identity is, needs to equal the same number that I used. So it needs to equal 9. So with adding, what could I add to 9 to keep it 9? The answer is 0. 9 plus 0 is still 9. So for adding, the identity is 0. Let's do the same thing for the subtracting. So if I do 9 minus what, would I still have 9? The answer is also 0. 9 minus 0 is still 9. So subtracting its identity is also 0. So this is what the identity is. So we need to figure out what the inverse of adding is. Like, how do I undo adding? Well, does anyone know if we have something getting added to x, how would you undo it? Subtracting. And if I'm subtracting something from x, how would I undo it? By adding. So adding and subtracting are each other's inverses. So I'm going to write that big right here. Adding and subtracting are each other's inverses. But let's talk about why. Because remember, I told you an inverse up here, the formula is that when I take some number, so I'm going to take some number, like 9, and then my operation, and my operation right here is adding, so adding, whatever my inverse is, and it needs to equal my identity. And remember, my identity for adding is 0. So it needs to equal 0. So what can I add to 9 to get out 0? Negative 9. So when I'm adding something and I minus away the same number, it cancels out, it eliminates. Which is why adding and subtracting are inverses. If I did the same thing over here, if I had 9 minus something and it had to equal the identity for subtraction, which is also 0, 9 minus what is 0? 9 minus positive 9. So don't forget this is a positive 9 that I'm subtracting away from this 9. So that means, again, subtracting and adding are each other's inverses because they undid each other and got this 0, which is the identity for adding and subtracting. So that's why they undo each other. Adding and subtracting always undo each other, and that's why. Let's do it with multiplying now. So we always have to find the identity first. So if I take 9, and if I want to multiply 9, so remember multiply in high school math, we use a parentheses. What do I need to multiply to 9 so that it stays 9? Because remember, the identity is some number that when I do that operation, it doesn't change the original number. So 9 times what is 9? 9 times 1. So multiplying identity is 1. To figure out the inverse, before I help you figure out why the inverse is the inverse, you should know what the inverse of multiplying is. Because what undoes multiplying? Dividing. Let's talk about dividing's inverse. So if I have 9 divided by what number will stay 9? Well, 9 divided by 1 is still 9. So again, 1 ends up being identity for division. So division's identity is 1 as well. So they both have the identity of 1. So then I'm going to prove why they undo each other, or why they're each other's inverse. So I'm going to write it big and bold. Multiplying and dividing are inverses. And here's why. If I have 9, and I want to times it to some number, and it's still going to need to equal the identity, which is 1, What can I multiply 9 by to get out 1? You would divide 9 by 9, because 9 divided by 9 is 1. But this will make a lot more sense if I turn it into fractions. So remember, 9 is the same thing as 9 divided by 1. And if I multiply it to some number, some fraction actually, we're going to make sure it's a fraction still, the answer should equal 1. Well, remember, a fraction that is equal to 1 means it's the same on top. Whatever is on top needs to be the same on bottom. Because if it's the same on top and bottom, the answer is 1. So if this top is 9, but this bottom's 1, if I want to make them the same, if I put the 1 on top over here, and then the 9 on bottom over here, if I flip it, this fraction over, then now, since there's a 9 on top and a 1, and there's a 9 on bottom and a 1, both times we do it. On top, 9 times 1 is 9, and on the bottom, in the denominator, 1 times 9 is also 9, and 9 divided by 9 is 1. So if I take out the unnecessary stuff here, so I'm going to do this again in a different color with the unnecessary stuff. If I have 9 and I want to times it to something, and I want it to equal 1. The answer here was the fraction 1/9. So what this is called, 9 and 1/9, are called reciprocals, because when you flip a fraction, it's called a reciprocal. So sometimes they tell you that if you want to write divided by something, if you want to write divided by 3, it's the same thing as multiplied by 1/3. And this is why, because when you're multiplying by the fraction 1/3, what you're really doing is you're dividing it by 3. Just like here, when I'm multiplying by the fraction 1/9, what I'm really doing is I'm taking 9 and I'm dividing it by 9, which is why it ends up being 1. So this is why, in this case, even though I'm multiplying by the fraction as my answer, what I'm secretly doing is I'm saying divided by 9, which is why multiplying and dividing are inverses. So quickly, it's important. So the two things we've talked about a lot so far are inverses and identities. Inverses are going to come up in just a second because we're going to use them to solve for x. But I want to talk about the identities real fast. Here's the thing about the identities. If I were to take a number like 8, if I were to take each operation like add, I can add 0 to 8 and it's still 8. Or this could have said subtract. I can also times 8 by 1 and it's still 8, because the reason why I could add or subtract 0 is because 0 is the identity for adding and subtracting. The reason why I could times it by 1 without changing it is because multiplication is 1 is the identity for multiplication. So then if I wanted to take this whole expression and divide it by something while still keeping the answer 8, you can always divide by 1 and it's still 8, because 1 is the identity for division. And if I had 8 things dividing into one group, there'd still be 8 of them. Therefore, these are all invisible things that we can always put there, but we never need to, because it's implied. It's implied that we're adding or subtracting nothing. It's implied that we're always multiplying and dividing by 1. So then, taking the same concept with exponents. So what exponent is currently on this 8 if there's not one there? What's the invisible exponent? The invisible exponent is always 1 because that means we have 1/8 being multiplied to itself, and that's just 8, which means the identity for exponents is 1, because if there's an exponent of 1, it does not change the number. So then, what's the inverse for an exponent? Well, to get there, I have to first start by teaching you a quick exponent rule. It's called the exponent on exponent rule. And it looks something like this. If I have some number, and it doesn't matter what number it is, so we're going to call it x. If it has an exponent on it, like 3, and then it's in a parentheses, and then that parenthesis has another exponent on it, like 4. The exponent on exponent rule says when you have an exponent on top of an exponent like this, you multiply them. So the answer is x to the power of 12. X to the power of 3, all in a parentheses, to the power of 4, first means that you have 4 of those parentheses. Then each one of those parentheses, each one of those x to the power of 3 means that there's 3 x's for that one. So that's what each x to the power of 3 means. So I can replace this one with 3 x's, this one with 3 x's, and this one with 3 x's. And now if you count, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And for that reason, the rule is when there's exponent on exponent, you get a multiply. So if I take some number and it's to the power of 2, I want to use the exponent on exponent rule to raise it to some exponent. We don't know what. Something's going to go right there, but it needs to equal, when we're all done, x to the power of 1, because that's the identity, is when the exponent's 1, which we talked about up there, because it's the secret one. So 2 times something needs to equal 1. Let's see what that is. Let's talk about that. So 2 times something needs to equal 1. Well, if you remember up here, it's not that it's 2 times something, it's that it's 2 divided by 2, but we write divided by 2 as multiplied by 1/2. So 2 times the fraction 1/2 is 1, because 2 is the same thing as 2 divided by 1, and then in the numerator, 2 times 1 would equal 2, and in the denominator, 1 times 2 would also equal 2, and then 2 divided by 2 is 1. Therefore, if I don't write this as like this, it's just a 2. 2 times 1/2 is 1. Another way to think of it is half of 2 is 1. So therefore, I need to raise it to the exponent. The inverse needs to be 1/2. And that's how you undo it, is you put both sides in parentheses and you raise them to the power of 1/2, because this cancels here. This cancels and just becomes this 1. So here's the thing though. If I go to Desmos, and let's say I take 9, and I raise this one to the power of 1/2. The answer is 3. But then if I take the square root of 9, look, the answer is also 3. And then if I did 16 to the power of 1/2, the answer is 4. But if I took the square root of 15 or 16, the answer is also 4. And here's why. It's because square root is the symbol that a mathematician's made up that means to the power of 1/2. They don't like the way this looks. They think that looks ugly. So they're writing it like this instead. And it's just a symbol. So swear to you, the square root means exponent 1/2. If I wanted to take x to the power 1/2 and then undo the 1/2, what can I times 1/2 by and raise the whole thing to in order to make it become 1? Well, the reciprocal, if I flip 1/2, it becomes 2/1. Remember, 2/1 is just 2. Which means, and this part's important, remember x to the power of 1/2 is the square root of x. Which means if I take the square root of x and I square it, it cancels. The square root with the square cancels because they undo each other. And then I'm just left with the x to the power of 1, but I don't have to write to the power of 1. Like I didn't have to write it here. So just like up here, when I raised it to the power of 1/2, note that it's the same thing that if I had x squared and I wanted to undo it, I can do it by putting it in a square root. And then the square root, because raising it to the power of 1/2 is the same thing as making the square root. So these cancel each other, the 2 and the square root. So then the answer is just x to the power of 1 as well, but you don't have to write to the power of 1. So the point here is that x squared and the square root of x are inverses. Don't forget the square root of x is secretly the same thing as x to the power of 1/2. Like those two are equal to each other. Which means if I have an x squared, to undo it, I'm going to use the square root and vice versa. We're going to look at that in a second. Finally, just quickly, the cubed root is the same thing as 1/3, which means the inverse is an x cubed. So x cubes and cubes roots, they undo each other. In the same way here, I want to say that if the thing in the square root has an exponent as well, because all of these had like a little invisible 1, like this x right here, secretly x to the power of 1, because if there's just one x. So that means the top number is the exponent on the x, and the bottom number is what the root is. So here, the exponent on the x is the 3, so it goes into the numerator. And then the 4 comes from the 4th root in the denominator. So for this one, the inverse is, and we'd have to basically take that 3/4, and then you just take the reciprocal of the fraction. So it would be to the 4/3. It just flips it. Just like here, 1/3 flipped is 3/1, but 3/1 is just 3. So it's always, the inverse is always the reciprocal of whatever the exponent is, except often we use roots instead of fraction exponents. So you just have to be able to go back and forth in between them and understand what they mean. All right, so we're going to do tons of examples of solving for x with each operation really fast. So whenever I solve for x, in order to cancel or eliminate a term, I have to do its inverse. So here's how it works. You always want to draw a line at your equal sign because it acts like a wall and it separates your two things in half. Then our goal is to solve for x, which means isolate for x, which means get x all alone at the end. So right now there's a -5. inverse of subtracting is adding, and adding 5 undoes the fact that we subtracted 5. But I always have to keep my equations balanced. So if I add 5 to the left half, I also have to add 5 to my right half. So then when I do the math, this x, nothing happened to it, nothing's beneath it, so it comes down. Minus 5 plus 5, they were inverses, so they eliminate, they cancel. And there's 0, but I don't ever have to write plus 0. There's no point of writing that. It's just nothing. So then the equal sign's still here, and then 12 plus 5 is 17. So the answer for this one is x is 17. If I were to do it with adding, this is x plus 4. To undo adding, we subtract. We have to do it to both sides. The x comes down. The plus 4 minus 4 cancels. Negative 10 minus 4 is negative 14. All right. So that was adding and subtracting. If I do it for multiplying and dividing, remember 3x means 3 times x. So to undo timesing by x, the inverse is division. So I'm going to divide both sides by 3. 3 divided by 3 cancels and becomes just 1x, but I don't have to write the 1. Negative 12 divided by positive 3 is negative 4. So in this case, x would equal negative 4. If any of these are confusing you, like the arithmetic, like why the answers are the answers, go watch warm-up videos on either adding and subtracting or multiplying and dividing if this is the part that confuses you. So when you have a fraction, remember fractions mean times by the top, divide by the bottom. So I'm going to start with the fact that it's dividing by 7. So to undo dividing by 7, I have to multiply this side by 7, and I have to multiply this side by 7. So multiplying and dividing are inverses, so these two cancel. So I still have the negative 4 and the x. And then on the right, 8 times 7 is 56. Finally, negative 4 times x, or multiplied to x. To undo that, I have to divide it away. Because negative 4 divided by negative 4 cancels and becomes 1x equals 56 divided by negative 4 is negative 14. So that was a multiplying and dividing one mixed. This one's just the square root. Remember, the inverse of the square root squared. So I'm going to put this side in a parenthesis and square it. And put this side in a parenthesis and square it. So this square root and squared cancel, so I'm just left with x equals, and then 5 squared, 5 times 5 is 25. And then finally, if I started with an x squared, to undo that, I could either do parentheses 1/2, but remember that's the same thing as square root. So I can square root both sides. Square root and squared canceled, so I'm just left with x equals the square root of 9. If you put it into a calculator, you'd get 3 because 3 times 3 is 9. But remember, it's always positive 3 and negative 3. Because when you take square roots, you want both the positive and negative answer. So that's how all the inverses work.